Hi, my name is Gelareh Meidanipour Lahijany. In this presentation, we want to talk about our paper entitled Structural Bug Localization using Graph-Based Deep Learning on UML class diagrams. The presentation is organized in 4 sections. We start with an introduction to bug localization and the application scenario. Then we explain about automated bug localization and how it is possible in model-driven engineering using software design modeling views like UML class diagrams. And then how we applied our approach identibug on the Java Development Toolkit project and its statistics. We also discuss an example of a bug report sample and its specifications. In the approach section, we explain about our prototype identibug and how it works in terms of its different components. In the third section, we demonstrate our evaluations and their analysis. In the last section, we will talk about conclusions from our approach. In the first 4 slides, we present an introduction. As we said, introduction includes topics like application scenario, automated bug localization, the related possible models, and the dataset we used. Our approach for bug localization can be considered as a tool within a bug fixing process. In general, a bug fixing process includes several steps. First, to identify a new bug. Second, to find the bug location. Third, to analyze the bug. And fourth, to fix the bug. Thus, there could be 3 use cases in this process. First, after identifying a new bug, a reporter writes a bug report. Second, to find the location of the bug, a developer has to search the source codes. In this part, there is a need to an automated bug localization tool which helps the developers to proceed their work more conveniently and also to save time and effort. Third, a developer must analyze and understand the bug to finally write a bug fix. Finally, the developer commits the bug fix into the project's repository, creating a new version of the software. In our approach, bug localization in model-driven engineering refers to the process of automatically finding the bug locations in a UML class diagram. In our case, bug localization is solved as a link prediction problem that predicts the bug locations as edges between a new bug report and existing classes in the diagram. The general overview of such a process is illustrated in the following figures. As it can be observed, the initial result is a rank list of model elements as bug locations, from which we generate a UML class diagram to visualize the bug location. This can help the developers in the process of analyzing the bugs or documenting them. We have evaluated our approach on over 5,800 actually fixed bug reports from the Java Developer Toolkit, JDT, using 90% for training and 10% of the dataset for testing our bug localization predictions. The average number of considered classifiers for the predictions is about 2,000, and the abstract syntax graph of the JDT class diagram contains about 300,000 nodes and 500,000 edges in the latest version. As you see, An example of a bug report with its specifications like bug report number, summary, creation time, status, creator, commit message, and discussion is presented. Generally, there are two methods for bug localization: static and dynamic. Static methods use traditional information retrieval models to create data model, such as statistical model provides embedding vectors and important information from textual data of bug reports and source codes. The dynamic methods apply AI algorithms like deep learning on a custom system model to create data model. After creating the data model, the next step is to predict the bug locations based on the data model. In the static model, to find the distance between vectors and then recommending the bug locations, a similarity measurement is computed. In the dynamic model, vectors from the data model should be given into a prediction algorithm to recommend the bug locations. For example, in our case, recommending the bug locations is performed by finding an edge between a new bug report and an existing model element in the bug location graph of the whole system model. Our approach, called IdentiBug, utilizes deep learning techniques to build our bug localization model. The embeddings of a bug report and each UML class are passed through a link prediction layer to specify the existence of an edge targeting a bug location. The result is a rank list of classes from which we generate a rank list of class diagram excerpts for supporting developers during bug documentation and localization. We describe our approach in terms of two main components. The first one is related to reverse engineering of the UML models, and the second one is related to our deep learning model called DLM, which includes two phases: node self-embedding and structural node embedding. Now we start explaining about these components. First, we do a step of reverse engineering to obtain the history of the so-called model in terms of a UML class diagram from the source codes in the corresponding repository. Additionally, we create a graph that stores information related to the model versions and bug reports. During the training of the deep learning model, we consider two versions of system model. One is the buggy version and the other one is the fixed version. The historical bug locations can be extracted from the changes which were applied between fixed version and its previous buggy version. The bug locations can be represented as references from a bug report to a model element in the system model's abstract syntax graph. Finally, all historic versions of the system model's abstract syntax graph are stored and accessible by querying a graph database. To evaluate our approach, we train our deep learning model with bug reports and historic bug fixes from the Java Developer Toolkit project. A bug report consists of textual comments as notes and the bug locations as edges pointing at classes in the diagram's abstract syntax graph. For node self-embedding, we use textual information from each node in the abstract syntax graph and create embedding vectors from a pre-trained word-to-vec model, and then compute some of the word embeddings. Then, for obtaining structural node embedding, we use inductive representation algorithm GraphSage. which gets the node self-embedding and performs neighborhood sampling. At the end, the node's structural embedding vectors are fed into the link prediction layer for localizing bugs and getting the rank list result. In the ranking result, we have the bug locations with their prediction probabilities. During bug report prediction, we take all UML classifiers of the current version of the system model as potential locations. So we process the input UML class diagram and bug reports to create pairs LR of the bug location nodes L and the bug report nodes R from the buggy versions. Then we compute a neighborhood sampling for both nodes in LR. For example, we collect the subgraph of nodes that are reachable within a certain distance k. The neighborhood sampling is performed by querying random subgraphs from the graph database. Our approach also allows to specify custom sampling queries based on the type of a node. From the rank list of classifiers, we finally generate a rank list of diagram excerpts for supporting the developers during bug documentation and localization. To get the rank list of diagrams, we iterate over the rank list of classifiers and collecting the surrounding neighbors of each classifier with a specified search depth and a given maximum number of classifiers per diagram. We perform two main experiments to evaluate our method, namely rank list of classifiers and rank list of class diagrams. In the first experiment, we simply compute a ranking including every single classifier in the system model's class diagram. In the second experiment, we compute a ranked list of class diagrams excerpts to represent potential bug locations. At the end, we visualize the experiments in several plots, considering top K ranking results in the right figure. Our evaluation metrics are MAP, MRR, and top K. MAP or mean average precision only measures the first relevant recommendation in the ranking results. MRR or mean reciprocal rank measures the precision of all relevant recommendations, and top K measures if at least one relevant location is contained in the first K recommendations of the ranking. The left figure shows the distribution of the relevant bug locations collected from all computed rankings. The top ones in our set of bug report test samples. The box plot shows the median of the positions of all relevant recommendations in the rank list of classifiers, which is about 223. That is relatively high and also contributes to the relative low MAP and MRR in Table 1. However, if we compare the distribution in Part B, we see that the median drops to 23 if we consider only the first relevant recommendation on the top of the rankings. We can see an improving effect for the rank list of class diagrams on the metrics of MAP and MRR shown in Table 1. Moreover, the top K metrics is close to the state of the art and has even a higher accuracy for top K of 10. The figure also shows how the top K results are affected by outliers, which is more significant for our diagram ranking compared to the plain classifier ranking. This evaluation gives initial indications for a promising research direction to recommend bug locations as structural diagrams. In this paper, we propose our approach for structural bug localization using graph-based deep learning on UML class diagrams. Results showed the efficiency of our approach, especially in the second experiment, which is the rank list of class diagrams. And this is a new way of proposing bug locations compared to state of the art. In future, we aim to enhance our approach by more fine-grained predictions and rankings of other types of bug locations, like operations and properties from class diagram, to further reduce the diagram excerpts shown to the developer. In addition, we want to give the developer the ability to customize the proposed diagrams consistently by adding and removing parts incrementally with respect to the diagram's well-formedness. Moreover, we plan to enhance our deep learning model by more sophisticated word embedding methods and testing different neighborhood sampling methods, like depth of the neighborhood subgraph and specialized queries for selecting the subgraph from the graph database. Furthermore, we plan to introduce additional modeling views to capture data flow and control flow during the reverse engineering of the system models. This is the end of our presentation. Hope you enjoyed it and thanks for watching.